Everywhere in the negatives, up until, but obviously not including 0, the y-coordinate is always going to be -1. So -3, -1, -2, -1, -1, -1, -2.5 will plot to -1. So this is essentially a horizontal line at -1, but with an open circle at 0. And then once we get into the positives, same thing is going to happen. It's just we'll be at +1. Open circle at 0 still, but then a +1. So this is what we would consider the parent graph of this function. It doesn't have like an official function type, it's not like a linear function or a quadratic function, but loosely speaking, we refer to these as jump functions, which I think you can see why from the picture that jump makes sense. So it lacks kind of an official function type vocab word, but I'll refer to these as jump functions. And like any other function, these can shift left, they can shift right, they can shift up, they can shift down, they can be stretched, and so forth. In looking at the limit information, what is our limit as x approaches 0? Does not exist. What is it if we're approaching 0 from the right? 1. What if we're approaching 0 from the left? -1, right? So it does have the one-sided limits, but not the overall limit because those disagree. What is the limit as it approaches 2? 1, right? So as it approaches 2 from the right and from the left, both of those have a y value of 1. And as it approaches -2, which is here, from the left and from the right, both have a y value of -1. Okay? So that is our parent graph for a jump function. What has this done? Right. Shifted which way? There is no asymptote. That's a jump. It's not an asymptote. If it was an asymptote, what would be the behavior as you approached it? It would be infinity, right? It's an undefined, but it's not an asymptote. Okay? But yes, g of x is essentially your f function shifted to the right 3 units, right? That's all they did is plugged in x minus 3 in for the x, which means it's shifted right 3 units. And if we're sketching it 1, 2, 3, yes, the jump does occur at 3. Correct. Absolute value over itself without the absolute value. So on this one, our limit as we approach 3 from the right. What do you think, Stephanie? Good. And Kyle, how about the limit as we approach 3 from the left? Good. And so the overall limit as we approach 3, Zach? Correct. The jump is. Correct. Because it'll always be a jump between 1 and negative. The next exercise looks totally different. X minus 1 over the square root of this quadratic. But if you take a closer look at that quadratic, it's factorable, right? X squared minus 2x plus 1 is the same as x minus 1 squared. And then again, this is going to bring us back to a point that I made back in September, something that I taught you that you really we kind of, as math teachers, held the wool over your eyes for a little while. What is the square root of something squared? No, that's the misconception. That was the way you've been misled for the past few years. Like, I'll give you the numerical example. What is the square root of -5 squared? So does that equal itself? Correct. So we talked about this equals the absolute value of itself. So in this particular case here, the square root of that binomial squared is x minus 1 over the absolute value of x minus 1. Now, what do you notice about this graph? Yes, but also the absolute value is now in the denominator, not in the numerator. Do you think that's going to cause any changes? You mean like flip like that? Well, the one way to find out to see what effect that might have on it is to just kind of quickly sketch a graph. Obviously, at 1, there's a breaking point. What happens at 2? If you plugged in a 2 to this. 1. What if you plugged in 3? 1. So it didn't really flip it at all, did it? Okay. So the parent graph of, I guess, 2 things to take from this. Number 1 is that this is a shift to the right 1 unit, which obviously we can see. The other is that the parent graph, whether it's written that way or it's written with the absolute value on the denominator, it's the same parent graph. Okay, that doesn't make much of a difference. Okay, and we've learned from the start of time that anything divided by itself is just 1. But because of that absolute value in there, sometimes we get positive 1, sometimes we get negative 1. So this being simplified, kind of written down to this, we didn't really simplify anything, I just rewrote its presentation. The limit as x approaches 1 from the right is still 1. From the left is -1, and therefore the overall limit does not exist. Okay, so that's your intro to jump functions, and those will come up on your homework, and that's a new type of graph and concept for you. This next example gets me into this unbounded thing, which we have done. This one is a vertical asymptote situation. Where is our asymptote? Right, not only is it at 0, but it's a double root sort of asymptote, which means what? Right, whether it's positive infinity or negative infinity, let's pretend we don't know yet, but it is going to be the same and working together on both sides. So as we approach 0, and we know as we approach vertical asymptotes, we approach infinity of some sort. That's where this unbounded terminology comes from in the title. I kind of put a star for the new concepts we were going to look at. This isn't really new, but I don't know if I've phrased it that way before. So they refer to that as unbounded because it's approaching not a number, but an infinity, and it's therefore unbounded. But obviously, if you're approaching from the positive side, it's going to be positive over positive, so that's positive infinity. And as you're approaching from the negative side, it's still going to be positive over positive. And so we're going to positive infinity on both sides. As far as a horizontal asymptote, it's small over big, so it's just 0. And so unbounded limits, therefore, don't exist. Okay? But we do give more specific answers if possible. So yes, this limit doesn't exist, but you're probably not going to see does not exist. You would see the more telling version of does not exist, which would be infinity. And we're able to do that here only because from the left and from the right, they're both the same infinity because of that double-rooted asymptote. Okay? So nothing really new there. This is a new concept here. So not a sine curve, but the sine of 1 over x. And we're going to do a table on this. I also think that we can think about it in a couple of different ways to shed some light on it. But we'll start with the table. And in this table, we're given our x coordinates because it would be too difficult. But 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi. What are these x numbers approaching as the denominator changes from 1 pi to 3 pi to 5 pi to 7 pi? Zero. Yeah, it's getting smaller and smaller. When your numerator remains constant and your denominator keeps growing and growing and growing and growing and growing, right? The number is actually approaching 0. And they have this approaching 0 because that's the limit we're after. What is the limit of this function as x approaches 0? Now, they chose these x's obviously because it's going to make our sine able to be calculated without a calculator. So it's really taking the sine of 1 over the x value, which is really the sine of the reciprocal. Yes? I'll show that out at just one time. So the sine of 1 over 2 over pi is the same as sine of pi over 2. It's just reciprocating that fraction. And we all know that the sine of pi over 2 is 1. And then the next one is going to be the sine of 3 pi over 2, which is -1. And the next one's going to be the sine of 5 pi over 2, which is a coterminal to this one, right? Pi over 2 and 5 pi over 2 are coterminal, so they're both 1. And then this is going to be the sine of 7 pi over 2, -1. And then obviously we can keep going with this pattern of our x coordinates infinitely. 2 over 9 pi, 2 over 11 pi, 2 over 13 pi, and it's just going to get closer and closer to 0, but our y behavior is not honing in on any specific number. It just continues to oscillate back and forth between 1 and -1, 1 and -1. So as our x's get closer and closer to 0, obviously they can't ever be 0 because we'd have an undefined, right? Sine of an undefined. Can't do it. And our y values keep bouncing back and forth, not really honing in on any specific value. So this limit does not exist. And we can see that from a table of values perspective. We will plot it in a minute, but before we do that, let's think about direct evaluation. So if I thought about the limit as x approaches 0 of the sine of 1 over, I can't do 0. But what happens to this as this gets closer and closer to 0? Don't worry about the sine part. As this number x gets closer and closer to 0, I'm going to have 1 over a teeny, 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 tiny number. 1 over 1/100th would be 100. 1 over 1/1000th would be 1,000. So this particular portion is approaching infinity, yes? And what is the sine of infinity? Well, there's no way to tell because you know your sine graph keeps oscillating back and forth forever. So as you approach, as this graph gets closer and closer to infinity, you keep bouncing back between 1 and -1. Does that make sense? So to think that when you plug in infinity, or when you plug in something really, 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 really close to 0, that you're taking the sign of infinity, you can't take the sign of infinity. Because 1 second later it will be 1, and then it'll be -1, and then it'll be +1 again, and there's just that constant oscillating behavior. The graph of this, to go to part B, to make you see what the graph of it looks like. I'm going to do my window from -pi to pi. And I'm going to do from -1 to 1 should be fine. Mode in radians, good. So this kind of freaks out a little bit. I went from -pi to pi as it approaches 0. And it kind of looks like it shot up, shot down, shot back up, shot back down, just like 2 or 3 times, right? That's going from -pi to pi, which is -3 to 3-ish. If I change my window and I go like -1 to 1 and look closer in at what happens, now it looks like it did it like 5 or 6 times. And this is a weird concept, but as you get infinitely close to 0, we kind of saw it on the table of values, it oscillates an infinite number of times in this little stretch here, right? Because you can get infinitely close to 0, like this is getting infinitely close to 0, which is a weird concept, but there's infinity in the unbounded sense where the numbers are getting larger and larger, but you can also get infinitely small, 1/100th, 1/1000th, 1/1,000,000th, 1/10 millionths. And again, I'll do it just one more time. If I go from -0.1 to +0.1, you're still going to see a crazy number of these things because it's constantly going back and forth between -1 and 1. So at any rate, the calculator almost can't do it justice because there's that idea of an infinity going towards 0. But the fact of the matter, this is an oscillating graph that kind of erratically goes back and forth constantly, and that's what I meant on the top by like an oscillating type of function. Does this make sense? Yes, no, maybe. Anything? Any questions, comments, concerns? Steve? Let me think. I love these questions because I don't know them off the top of my head. I have to think about them so you get to see it raw. Well, as you approach 0 here, you also have the undefined issue. So you could do a table of values, or we could just explore it. So if I did the cosine of 1 over x, let me go -pi to pi first. Yes, it does. What do you notice that's different about the graph, though? Yeah, why is that? Even function, right? Symmetrical to the y-axis. So if I kind of zoomed into -1 to 1, I'd see, yep. But that, to our point about even and odd, cosines are even, sines are odd. So that's kind of an interesting thing that you see. But yes, your answer is yes. It does have that same behavior. Okay, good question. Okay. Anything else? All right. And then this last example here is a limit as x approaches 0 of a log function. So you may or may not, probably didn't miss it too much, so you probably didn't notice, but your pre-calc book never really had you looking at log graphs at all. And the calc book, I mean, it's a realistic type of function, so you're going to see more of them, and they're a little tricky because A, we don't love log and exponentials at all, and B, then we throw the limits on top of it. But at the end of the day, we would kind of treat it the same. You try to directly evaluate, and so if we were to do that, we would get the natural log of 0 plus 1 over 0, which is the natural log of 1 over 0. And what is the natural log of 1? No. What base does the natural log have? E. So e to what power gives you 1? Okay. So per usual, we get this indeterminate case, which means we can't conclude anything about the limit. We have to look more deeply into it. So we start by doing this with a table of values. What happens as we approach 0? So I'm going to use the calculator to type this function in, and I'll look natural log of x plus 1 divided by x, and my window I'll do from -1 to 1 is fine with me on my x-axis because I'm trying to approach 0. On my y-axis, I don't know what's going to happen, so I'll do -10 to 10. And really, I mean, I can see from my graph, I think, what's happening as it approaches 0. What do you think the limit is just looking at the graph now? It looks like it's about 1. To fill in our table of values, I'm going to use my second trace feature and the value, and I'm going to plug in -0.1, and I get 1.05. And then I'll do second trace again, and I'll do -0.01, and I'll get 1.005. And then again, plug in -0.001, and I get 1.0005. So we can definitely see that this is on the decline towards 1, coming from the left. And on the right-hand side, if I do 0.1 first, I'll work outside in. I get 0.95. Second trace again with 0.01, I get 0.995. Second trace one more time, 0.001, and I get 0.9995. Clearly on the incline towards 1. So our table of values backs up that this limit is 1. This is something that we don't know how to graph, so we would have to rely on the table of values for that, or on the look of the function. You will notice in your calc book, can I see your book for a second, Connor? That next to certain sections, there will be a little image of a calculator. Not so much here. Where it's not a calculator, I guess. It's like a little thing like this. Anytime that image is there, it's indication that use your graphing calculator. Feel free to use it to help you. Same thing here, but like a lot of sections don't have that. So, but then that's kind of funny that they don't have that picture there, because they do say it in the directions. Use a graphing utility. Use a little common sense. Of course you have to use a graphing utility. No one's going to ask you to plug 3.99 in and not have one. So, but as we move forward in the book, you'll see this icon a little bit more. And that indicates that you can and should feel free to use your graphing calculator. Because a lot of this is going to be kind of exploring similar concepts, but in what circumstances do you need your graphing calculator, or you need a calculator, and then in what circumstances you won't. Oh yeah, pass your quizzes forward, please.